We also have a sum, difference, and constant multiple rule with derivatives like we did with limits, and that's actually why. That's where they come from. So the derivative of the sum is the sum of the derivatives, if each of these derivatives exist. Likewise with the difference. The constant multiple rule tells you that you can factor out the constant and just take the derivative of the function. But now that's where it stops as far as getting our laws from the limit laws. The product and quotient law does not apply here from limits. Don't try to do that. A lot of people try to do that. That's a common mistake. The derivative of the product is not the product of the derivatives. We can use all these rules about the power functions and the sum, difference, and constant multiples to find derivatives of complete polynomials, because polynomials are just sums of power functions with integer exponents. So, for example, I differentiate this function, and I can differentiate term by term because of the sum and difference rule. So the derivative of 2t cubed is, first I can factor out that 2 by using the constant multiple rule. And then I can take the derivative of just t cubed. Again, I bring down the 3, subtract 1 from the power. And I wind up with 6t squared. Same thing with the next term. I factor out that constant. I take the derivative of just the power t to the second power. I bring down the 2, subtract 1 from the exponent. 6t. And then with 4t, I just have the derivative of 4 times the derivative of t, which is just 4 times 1, or 4. And then subtract them as they were in the original function. So I could have a function like this where it's a mixture of positive and negative powers. And the same thing applies. Differentiate term by term. So another example that you'll see in the homework is like find the points on the graph where the tangent line's horizontal. So you translate that to, oh, where's the tangent line horizontal? That's where the derivative is 0. So you take the derivative of this given function, which we found in the last slide, and you set it equal to 0. And then just going back to algebra, using the quadratic formula, these are the zeros of that function. And so you can see the derivative is this parabola, and where the zeros are. And those correspond to the x values for this local max and local min on the original function. Now let's look at the exponential function. So remember, the basic exponential function is just b to the x, where b is some number that is greater than 0. So if we apply, we're going to apply the difference quotient to that, but before we do, I want to point something out. So if f of x is b to the x, let's first find f prime of 0, and the only reason I'm doing this is because it's going to be one of those things that we need to use later. So when I apply the difference quotient at x equals 0, I get this limit. The limit as h goes to 0 of b to the h minus 1 over h. So we're just going to put that aside right now. And now let's look at the general derivative. So again, I have the difference quotient. I can't really do much with this, except I can factor out that common factor of b to the x. But now notice that this limit is in terms of h. This b to the x isn't really coming into play here with this limit. H is what's changing. So I can actually kind of treat that b to the x as if it were a constant, and I can factor it out from the limit. So I have b to the x times this limit. And this was the guy that we looked at up here. So this is, the derivative is b to the x times the derivative of this function at 0. I know that the derivative of the exponential function is just the exponential function times some constant value. Remember, f prime of 0 is an actual number. I'm plugging in 0 to the derivative. So this is telling you that the derivative of the exponential function is a constant multiple of the exponential function itself. What's f prime of 0? Well, that of course depends on what b is. So let's go back and look at when b is that constant e. So remember, in the last section we looked at the graph of f of x equals e to the x, and we saw that, or we kind of guessed or surmised that the graph, and then of course we verified it with Desmos, the graph of the function of the derivative of e to the x looked just like the original function e to the x. Going back to what we just saw, that the derivative of the exponential function is just a constant multiple of the exponential function. That means that the derivative of e to the x is just e to the x times f prime of 0, which is just this derivative evaluated at 0. So you're not expected to know this, but f prime of 0, or the derivative of e to the x when evaluated at 0, is just 1. So this all boils down to showing that the derivative of e to the x is just e to the x. F prime of 0 is 1 only when the base is e. We'll see later on in the course that this constant depends on what the base b is. The last couple slides may have been unnerving. Good news is that actually doing the problems, it's just a lot easier. So let's look at some examples. So f of x equals e to the 5th. Okay, that's just a constant because e is a constant. So the derivative is 0. G of t equals 4e to the t. I'm going to use the constant multiple rule, right? And that's just, this is 4 times the derivative of e to the t. But the derivative of e to the t is just e to the t. So this derivative is equal to the original function, 4e to the t. And now let's look at another one, f of x equals e to the x plus 1. Well, does that rule apply if the power is not just x? We don't know. But what we do know is that we can use algebra to turn e to the x plus 1 into e to the x times e. So we're using our laws of exponents from way back. And remember, e is just a constant. So this is just a constant multiple of the function e to the x. So remembering that the derivative of e to the x is just the constant times the derivative of the function. And it boils down to this is just e times e to the x, or e to the x plus 1. So we're seeing again and again where the derivative is equal to the original function.